So now that we've taken a look at all these different properties here and tried to understand a little bit about what each of them says, let's try to put them to use in a specific example. Let's take a look here at example number 1. Suppose that we have a function that is continuous at all real numbers, and that it's the case that when I try to find the area under this function, from 2 over to 6, I get a grand total area of 1. Remember that I need to be looking at this entire set of symbols here as kind of one symbol. This is equal to 1. And so our question is going to ultimately be, can I determine this integral here? Notice that this is really helping us to address a question again that we left off with in the last section. If I come across a really difficult integral, are there other ways that I might be able to start trying to think about how to evaluate it? Well, what we're seeing here is that with these properties, if I know something already about an integral that I've calculated, if I see maybe a slight modification of that integral, maybe I can use the above properties to compute it very quickly, as opposed to setting up a big, giant, scary limit and working with all those sums like we did in the last section. So let's see how we might be able to take this integral here and work with it. All right, so here's the first thing that I might note. If I'm working with an integral that goes from 6 to 2, I can already tell that something's a little bit strange in that my bounds are kind of in the reverse order of what they would typically be in. So one thing that I could do right away is I could go ahead and I could use property number 2 from up above. And I could say if I want to flip my bounds around, I just have to make the total amount of area that I have negative. So I could change this to go from 2 to 6. Okay, so I'm going to rewrite what I have to look like this. I could now see that, oh, there's actually a negative 1 on the outside of this integral. So if I wanted to, I could use property number 4 and say if there's a constant on the outside, I could move it inside, or vice versa. And so in this case, I'll take that negative 1 that's out front and I'll kind of put it inside. And notice I'll end up with a 3 times an f of x minus a 2. Okay, so I have this. Well, what property can I use now? Notice I'm getting closer to kind of being able to use this portion, but since this is all one symbol, and I don't see that exact same symbol down here, I can't replace the value of 1 yet. Well, maybe I could make use of property number 6, which says if I have a formula minus another formula that I'm integrating, I can separate that into 2 separate integrals. So maybe I can separate this then into an integral from 2 to the 6 of 3f of x. Don't forget you need the dx on there. And then minus an integral from 2 to 6 of 2 dx. Well, what can I do with this? Oh, notice here I could take this 3 outside, and I could make this 3 times the integral from 2 to 6 of f of x dx. And over here, I can actually make use of another property. Notice I'm just integrating a constant. I'm working with something like property number 3. I have a horizontal line up at the height of 2. And I'm integrating from 2 to 6. So I know that the picture that I'm working with there is going to be just a rectangle. So finding its area should be easy. It's going to be a rectangle with a height of 2 and a width of 6 minus 2. All right, we're almost done here. Notice that I finally have here the exact set of symbols that I was given in the question, which is that I have an integral from 2 to 6 of f of x dx, and I know what this whole set of symbols is equivalent to. It's the same thing as the value of 1. So now I can see here that what I'm really going to end up with is 3 minus the value of 8, and so I end up with a total value of negative 5. If this integral was already evaluated and found to be 1, then this modification is automatically going to be equal to negative 5. And notice again, that allows us to save time, because if this was again something that I had to set up with a big limit as n approaches infinity of a giant sum, right, with all this stuff, and then I had all these other things in here, right? Like, if I did all of this work to finally reach a value of 1, now I've been able to effectively skip all of that work, which is great. I can use these new properties to help us understand how I might be able to more quickly and easily arrive at a new solution. Let's take a look now also at example number 2. Notice here I'm given 3 pieces of information. If it is known, or actually, sorry, only 2 pieces. If it is known, though, that the area under the curve f of x from 0 to 10 is 17, and the area from 0 to 8 is going to be 12, can I find the area from 8 to 10? Okay, well, again, sometimes a picture here can definitely help. Notice I'm talking about, I know areas from 0 to 8 and also from 0 to 10. So I know that the area from 0 to 10, this much area in here has an area of 17. However, the area from 0 to 8 only has a total area of 12. So how much area must there be from 8 to 10? Now, this picture kind of illuminates this answer very, very quickly, and you might be able to spot it. Very obviously, the answer would end up being, if this is the space from 8 to 10, then this area would have to be 5, because 12 plus 5 has to make 17. Now, while here the picture is really great, just let me caution you that sometimes a picture may not always be the most illuminating way of dealing with this. So here's what I would tend to do most of the time on most questions. This is a great time to go ahead and use the idea that if I took the area from 0 to 8 and added the area from 8 to 10, that's the same as grabbing all the area from 0 to 10. Notice if I wrote that out, that would say, if I go from 0 to 8, I find the area under my function from 0 to 8. If I add on to that the area from 8 to 10, I know that that should equal the area from 0 to 10. Notice I'm writing this out symbolically as opposed to pictorially. But notice that the reason that the symbolic representation is useful is because I was given information in a symbolic form. I actually can see here that I've set up a little equation. And I know that this integral from 0 to 10, this part over here, is the number 17. I know that the first part from 0 to 8 is actually the number 12. And I have this leftover part here that I don't know the value of. But notice I can quickly see it. If I treat all of this as one distinct variable, then I can imagine solving for it, just like I would in an algebra class. I could say subtract 12 from both sides, and I end up with that this integral has to be the value of 5. Again, that's exactly what we saw here in the picture, but being able to set things up in this kind of more algebraic, symbolic way is going to be crucial to understanding questions that are slightly more complicated. With that in mind, I'd ask you to go ahead here and try to take a look at something like example number 3. Go ahead, pause the video here, and see if you can take what we've learned so far with the properties and what we've demonstrated so far in examples 1 and 2 to see if you can try to answer this question on your own. And when you unpause the video, you can watch me work through the solution. Okay, so here's what I ended up with for this particular question. So I could start by noting that it would be definitely possible to separate my integral here into 2 different integrals. An integral of 2 times f of x plus an integral of just the 10. Now, I know I can take the 2 out of this integral. So this is an integral of now just f of x. And I know that over here, this is just going to be 10 times 5 minus 3. It's going to be a rectangle that's 10 units tall and apparently 2 units wide. Now, I'll notice that I don't have this particular integral in here. I don't have an integral that goes from 3 to 5. But I can easily see here, if I just think about a quick number line, if I put the values 1, 3, and 5 on here, I can see that if I find the area from 1 to 3, and I add the area from 3 to 5, I end up with the total area from 1 to 5. Or another way to think about it is, if I find all the area from 1 to 5, and I erase off the area from 1 to 3, I will be left with the area from 3 to 5. And so I'm going to go ahead and express it like this. In place of this integral here, I'm going to go ahead and say I'm going to find all of the area from 1 to 5, and I will chop off of it the area from 1 to 3. If I think pictorially again about what's going to be left, if I found everything from 1 to 5 and I erased the portion from 1 to 3, I would be left with just 3 to 5. But of course the value of doing this is that I have values for each of these. This is 13 minus 4, and it looks like at the back I have plus 20. So 13 minus 4 is 9. 9 times 2 is 18. 18 and 20 should be 38. So you should have gotten down to a final value here of 38. You can see here that obviously making this switch here from the integral of 3 to 5 to this subtraction is much, much easier to do again if I can understand, maybe pictorially as well as symbolically, what I need to do to find the area that I'm actually looking for, which was this area from 3 over to 5.